much. First, thank the organizers for inviting me here. And I apologize, this talk is going to be about matrices. The convexity will be running throughout in the background, but on the face of it, mostly matrices. And actually, the title does not reflect the main idea. What is really the main objective of this project is to venture in a new direction of non-asymptotic random matrix theory, namely super exponential probability bounds. But before I talk about super exponential bounds, let me talk a little about what the non-asymptotic theory deals with, because this is not the main thing of the workshop. We are going to discuss random matrices, so the matrices with variance ensembles of matrices with random entries. And the classical random matrix theory studies the limit laws of the various spectral or geometric characteristics like eigenvalues, eigenvectors, etc. Here we are not going to consider limits as the dimension of the matrix goes to infinity, but we'll fix a large dimension and try to get explicit bounds. And let's focus for a moment on square matrices. So A is n by n matrix with, say, independent identically distributed entries, and there are results which are valid with high probability. Let me give you a few samples, but before that, why do we need such a theory? In applications, say in geometric applications, the image of A models a random subspace, and if we want to consider a random subspace of a normed space of dimension n, we cannot change the dimension of the subspace in the middle. The same about computer science problems where let's say we solve the system AX equals B. If we try to solve it, we cannot change the dimension of A. So let me give you a sample of results first. Independent and identically distributed entries. Then, if the entries, say, are bounded, then the probability that the operator norm of A is greater than c square root of n is less or equal than e to the negative c. And in this inequality and throughout the talk, c capital, c small, etc. denote absolute constant. I don't care about. And A is the operator of the spectral norm. Second, let A be matrix with IID, say Bernoulli entries, let's say Bernoulli 1/2 entries, then the probability that A is singular, in other words, the determinant of A is 0, is exponentially small for C less than 1. This was a breakthrough result of Kahn, Lellouche, and Semeredy from 4. And recently, Konstantin Tikhomirov found an almost optimal constant C, namely less or equal than 1/2 plus O small of 1 to the power n. Tikhomirov, and if we talk not about the singularity but about the smallest singular value, then the probability that the smallest singular value of such matrix is less or equal than T is bounded by Ct plus e to the negative Cn. This was proved by Vershin and his collaborators some years ago for the matrices with ID entries, and recently Campos, Jensen, Michelin, and Sasrabude proved it for the matrix with ID entries and which is symmetrical. So what's common among all these bounds? If you look at the right-hand side, you see the exponential term everywhere. And this exponential term is really ubiquitous to the theory. You cannot drop it, for example, even in the nicest possible case here, when the entries are IID normal random variables, this inequality is violated if you want the bound probabilities by something like the exponential of negative n to the 1.5.
Mark, I'm so sorry to bother you, but in this one, when you say just ID entries, you mean zeros of Gaussian.
Yes.
You can't quite.
Yes, right. I said bounded in order not to introduce some Gaussian. Yes, mean zero is essential here. And in this example, the picture is even worse. You cannot go beyond, let's say, take Bernoulli random variables. You cannot go beyond 1/2 to the power n, because the probability that this matrix has two identical rows is 1/2 is greater than 1/2 to the power n. Same as here. So these terms are necessary, and we used to consider them as necessary.
So I'm so sorry again to bother you, but about this one, so sub-Gaussian is actually, it's pretty much even only if, is that correct? That you cannot have, if you have ID means zero entries, in order for this to...
Yes.
This implies sub-Gaussian back, right?
No, one correction. If you have ID copies of the same random variable, if you cannot change the random variable depending on it.
Yes, no, that's what I think.
Yeah. Good. So we have this exponential term, and this is a necessary evil. But now let's ask ourselves what happens if we want to venture beyond it. Let's say to these probabilities. First of all, I cannot make any claims that the matrix will be non-singular. It will be obviously singular if you exclude only such probability. And moreover, it may be significantly more singular than just the determinant is 0, it may have low rank. So let's ask ourselves, how does the rank deteriorate if we want to exclude only events of super exponentially small probability? It's pretty easy to answer this question. Let's start with this result, or in general, this result with t equals 0. And we see that the matrix is non-invertible with exponentially small probability. What does it mean? The matrix is singular if one of the columns is linearly dependent on the other. And this fact, this event occurs with exponentially small probability. But let's say that I want the probability that the rank of A is less or equal than n minus k, and k is a relatively large number. So what do we have? We consider our matrix and separate n minus k columns, and the rest are dependent on those. The fact that the event that one column is dependent on these will be exponentially small in n. The columns are independent. It's less or equal than exponential minus c and k. We have k. Okay. The fact that you don't trust me is very good, because this is a gross cheating.
No, I'm not sure I understand your argument.
The argument. So the event that this column depends on n minus, linearly depends on n minus k. For this is exponentially small in n. These columns are, the columns in this part are independent. So it's e to the negative cn to the power k, which is e to the negative cn k.
Do you not have to multiply with n choose k, something like that?
You have to, but n choose k is negligible compared to this number. You have to be careful with the brackets. We'll see later on what the problem is. Okay. So I want this for k large, for k dependent on n. Say, as I said, k is square root of n, for example.
But you're not independent. Like, you're looking at singularity probability of this matrix with this column and with that column and with that column, and you say you're multiplying them.
No, I condition on that. And, I'll return to this example a little later. Okay, so this is what I mean by super exponential probability. Saying that, I have to explain two things. First, why bother? It's such a noble goal to write another paper. And second, why this is not trivial. We already proved it.
I think this is called a physics proof.
Yes.
Because they're not really independent, right?
No, they are independent.
They are
Other events, there are other events.
They are independent. So let me start with the first question. Why bother? And this is the question actually comes from computer science, and this is how I got into the super exponential probabilities. The question comes from Feige, and it follows his paper with Lellouche. The paper is about quantitative group testing. The quantitative group testing can be recast as the recreational math problem that everybody saw in high school or in middle school. You have a bunch of coins, and K coins among them are counterfeit, they are lighter than the usual ones. You take a sample, you weigh it, and this weighing determines the number of counterfeit coins in the sample. Then you repeat the process and you want to know the minimal number of samples to determine the set of counterfeit coins if you know their number. The modification that Feige and Lellouche considered was that the samples are chosen randomly and independently by Bernoulli selectors, and they actually found a bootstrap method for this. You don't have to determine the set of counterfeit coins if you have an algorithm which with high probability determines the set larger than counterfeit coins, constant times larger, then in roughly the same number of weighings you can determine the set itself. The problem was that this was not an unconditional statement, it was a condition on a conjecture. This is Lellouche. Let's say M be an M by M matrix where I consider N the matrix is fat, the number of columns is much larger than the number of rows, and with ID Bernoulli entries, I take any subset I of 1, etc., and any subset of columns of size n, then the rank of the submatrix M restricted to the set I is greater or equal than n minus c log n capital. So if we have this super exponential bound, then
something expectation or
with high probability.
and P is a constant, doesn't
P
it?
is a constant. If we have this bound, then verifying conjecture of Feige and Lellouche is one line. Let's see how many such matrices we have. We have n capital choose n small matrices, and we know that the probability of having rank n minus k is exponential minus c n k. We need this number to be much smaller than 1, but this number is exponential of negative n log e n over n minus c n k, let's be generous. I said that n capital is much greater than n small. So k equals c log n would do. So if we know super exponential bounds, we can verify this conjecture.
Just minus should be plus.
Inside
Yes. Good. Of course, this can be an overkill. These matrices are dependent on each other, and I treated them with the union bound. But actually, you cannot do better. One can prove that the probability that there exists a set I of cardinality and with the rank of I less or equal than n minus c log capital is at least 1 minus e to the negative cn if n is large enough, for example, as greater than n to the 1.1. So, morally, this union bound is necessary, and we need, we indeed need this super exponential bound. Okay. So, I hope this at least partially answers why this is interesting. There is another part to the answer, but
They really care about linear independence over the reals or the field of two elements for their use?
I think of the reals, but I don't want to put my head on it. Let me check with the...
For the field of two elements, and this is also a coding theory question.
Okay.
The dual of the matrix gives you a good code.
Good, then I'll have to talk to you.
But I don't know, but can you get bounds for linear independence over the field of two elements? That's more than linear independence over the reals.
Yes, no idea, because I didn't think about this question, but I'll have to talk to you about it. I simply didn't know about this direction. Now, so if we have this bound on the rank, we are in a good shape. So why this is non-trivial? How do we kind of prove this? We started with the fact that this column depends on n minus k first with exponentially small probability. Then I condition on the first column. And when I condition on them, I have to throw away an exceptional set. What is the size of exceptional set is easy to guess from the estimate we used. It was exponential, so the exceptional set is going to be of exponentially small probability. Again, in our usual life, the exponential small probability is nothing, we ignore it. Here we cannot, because this exponentially small probability will add an exponentially small term e to the negative cn, which is much greater than what I want to obtain. And this returns me, so we really have to prove this theorem. And this returns me to the first question, why it is interesting. If we try to prove it, it turns out that all the facts we take for granted in non-asymptotic theory are no longer true. The first thing we want to approximate. For example, if I consider the smallest singular value, it's I consider a vector x in the sphere, and I consider the norm of a x. I cannot consider all the points on the sphere at once, so I take a discretization and I approximate. When I approximate, so this is greater or equal than the norm of a y minus the norm of a times the norm of x minus y. When I use this approximation, the norm of a pops up. And we say that it's square root of n and forget about it forever. Here, as we said, we cannot. This quantity can be much larger. Actually, this is the most innocent obstacle, and this obstacle was can be treated. There is a tool which was brought into random matrix theory by Galina Lifshitz, the random rounding, which in a sense allows to replace the norm of A, the operator norm, by the Hilbert-Schmidt norm. And Hilbert-Schmidt norm is much more concentrated. The Hilbert-Schmidt norm is, the square of the Hilbert-Schmidt norm is the sum of the squares of the entries. So this is the sum of independent random variables. The sum of independent random variables is excellently concentrated. Good. So this is the most innocent thing. But what is really behind the obstacle, which is really major in this problem, is the arithmetic structure. The arithmetic structure was already made this appearance in all these papers, but here it's going to be more involved. So what I am talking about? Let's do this exercise. So, how we claim that this the probability that one column depends on the other is exponentially small. Let's denote the columns by A1, etc., A n minus k, and etc. And so we want the event E, say that the column AJ belongs to the linear span of A1, A n minus k. For J greater than n minus k. how can we recast this? Let's call this space F, and if AJ belongs to F, it means that for any U in the sphere, if U is orthogonal to F, then then the inner product of AJ and U has to be 0. So what is this inner product? Say, K, A, I, J, U, I from 1 to n. This is a linear combination of IID random variables Aij. And if I take a generic vector U, then the probability of that A, J, U is 0 is going to be exponentially small for a generic U, whatever it means. And if we know that with high probability, the space F orthogonal to F contains a generic vector, then we can condition on this event, and then for a single J, this is like this, this is exponentially small. So if I take it for all J's, this is going to be what we need, exponential of negative Cn to the power k. Which means that the only thing we need here is to show that with high probability the subspace F perp contains a generic vector, a vector with no arithmetic structure. The problem is that with high probability means that with
exponential.
A super exponential probability. And this is too much to wish for.
How can you possibly do it?
It is not. We have to compromise on a more moderate goal. Nevertheless, there were and there are results on the probability of the small rank. The first result was obtained about a year ago, slightly more than a year ago, by Jane and Sonny. And if A, I, J, if the entries are IID, Bernoulli P, and something then the thing that we need this would have been the end of the story, but
And,
sorry,
and what?
the problem is with that.
But the thing is that if without and, if you take Bernoulli matrix, can't you just show that you are going to have necessarily exponential probability? Am I missing something?
In a minute. So the and was and k equals constant. And this can be, if you go with Jane and Sonny method, this cannot be relaxed because they proved exactly that the subspace F perp has a vector without any arithmetic structure. Actually, their result for Bernoulli P is more precise than I formulated. This probability is not just e to the negative cn, it is the probability of whatever is less or equal than 1 minus e plus epsilon to the power n k for p less than 1/2 and epsilon positive and n greater than n0 of epsilon and k. As soon as k starts growing, you cannot control this. And the reason that you cannot control it is here. Okay, I have 2 minutes left, so let me make the last 2 minutes finally formulate what I wanted to say, and here is the result. Theorem, let A be an matrix with independent, identically distributed, if you wish, sub-Gaussian, but if you don't want to bother with the definition, bounded entries, and then for any k less or equal than c square root of n, the probability that the rank of A less or equal than n minus k is bounded by the exponential negative c and k precisely as we want. Okay, my time is up.